Gellért Máttyus joined Continental's Artificial Intelligence Competence Center in Budapest, Hungary, where he leads an R&D project about the perception system of automated and self-driving cars. Gellért, the stage is yours.
Thanks for the nice introduction. I'm from Continental, and I will talk about the fusion of deep learning and classical methods in AI. And I work at the Continental AI Center, and we are working on solving problems related to automated and self-driving problems. So during my talk, what I will address that usually now deep learning became a really big hype because it achieved very good performance in very difficult tasks, which we considered earlier as not really possible to solve. But now comes the question that also we had like earlier solutions, which were more about leveraging our prior knowledge about systems. So I call these now these more classical methods, which are in many cases are based on mathematical optimization methods. And then the question arises, if we have to tackle some problem, should we use these older methods, or should we rely more on deep learning and these more data-driven methods? And in my talk, I will take you to a small journey where I will start from really the evolution of science and how it will then turn into, there was a little bit of change between the paradigm into getting to deep learning. And also I will show a toy example to get really something, a specific example, how we can better understand these concepts. And then I will also mention I mention briefly what the applications are in self-driving. Okay, and first, because my field is related to automated driving and especially about computer vision, so I shortly introduced these fields. So assisted and autonomous driving is now a very rapidly evolving technology with the promise that we can sit into the car eventually without any driver. But achieving this is a longer journey. And so in the community, what they defined as like 5 levels of autonomy. And actually it's like 6 because the level 0 is like not having autonomy at all. And I just will briefly introduce what these are. So level 1 autonomy is, so usually when we drive a car, we can control a car along kind of 2 dimensions. One of the dimension is like the steering wheel, where we can control the car in a lateral direction, and then we have the brakes and the gas, which can control the car in the longitudinal way. And during L1, we can only use one of those. I mean, the computer, the car takes over one of those, but the other is still driven by the human drivers. And then in the next level, in the level 2, we have that the computer can control both of these. And this is, but we have the restriction that we still need to, that the human, it still needs a human supervisor. And if there is any problem, the human driver is still responsible and they have to be able to take over at any moment. And then that's where we arrive to level 3, where it's already allowed that the human driver can do something else, for example, read a book or watch a movie, but in a given time, for example, in 10 seconds, a driver has to be able to take back the control. So in this case, still a human driver is sitting there in the car. And then a next exciting level is like level 4. It means in this case already we have this that there is no more human driver needed in the car at the steering wheel. So you can basically get a car which drives really without the human inside of it. But it comes with some restrictions. And one of those restrictions are that it's only functioning in a limited area or under limited conditions. A good example would be like that this only functions in a given neighborhood of a city. And if there is some bad weather, some rain, snow, then this kind of automatic service is shut down. And this way, this kind of technology is very suited for more like not really a product which you can buy, but more as a service. Just imagine a robot taxi where you can just, as normally you would summon a taxi to you, but in this case, you get a taxi without a driver. And then level 5 is basically where you get the same level of autonomy as in L4. So there is no driver needed in the car, but it can drive anywhere, anytime. And that's some big challenge. And this is also more into the future. And now companies are more concentrating on the previous ones. And also like Continental is like targeting the level 1, level 2, level 3, where we can provide systems to car manufacturers today. And some of the functionalities which has to be solved and also what Continental provides are, for example, emergency brake assisted systems, which you can avoid collisions, accidents, and by this we can save human lives. Also some example for functionalities are lane keeping assists or detecting traffic signs, which can give us information if we are over speed limit or not. One important application is like automated parking. So we can basically, the car can park itself, and also how these systems can get more and more advanced. In the future, we can just, for example, get out of our car in front of our house, and then the car can park into our garage by itself. And then also one of these technologies to mention is to have like driver monitoring. For example, the application could be that if a driver would fall asleep behind the wheel, the system can make an alarm. So this is also one way to reduce fatalities on the road. And here I go towards like that such systems need sensors. And usually these cars are now equipped with many different sensors. And one of those are, so an example are, for example, LiDAR or radar. But here, one very important sensor, this is also what I will focus on, is like cameras. And also, but my colleague will also, in a later presentation, we'll also talk about a little bit more methods about LiDAR. So if you're interested in that, I will recommend that presentation. And yeah, what about the cameras? So they are very important because they are pretty low cost. And one reason is for that, for example, cameras can be found in many devices. Usually everybody has a smartphone, and nowadays a smartphone contains at least 2 cameras. And for this also, it can be made in very high volumes, and the cost can be kept down. And also, yeah, here's an example for such a camera made by Continental. And what is important, in the camera functions very similar to a human eye. And this is also one reason why we like to have cameras in our phones, because we can just take one image with a camera, and for humans, we can really understand that image. If you would take an image with a radar or a surround view, it would be much more difficult to achieve the same things. And just briefly, what a camera does is a camera, we can consider it as a device to measure angles in 3D. So what is important that if you have a pixel in a camera, you can tell kind of from which direction that information comes, but you cannot measure how far it is. And this leads us to a well-known problem when we deal with systems with cameras, which is about like reasoning about how far an object is, which is in the image. And one good example for why this is a challenge, we can because once we have an image, for example, we can see a car. Actually, just from a single information, it could be a car, which is like a toy, a matchbox car, and it's very close to us, but it could be a real car and then it's farther away. But a single image, there is no information which could resolve this. And then the field which tackles the problems of these, so interpreting camera images, is called computer vision. And what's the purpose is to be able to reason, to understand the images similar as humans do. And one important aspect is that this was really one of the core applications which pushed machine learning, and also by this deep learning. And the reason for that is that we humans can understand images very well. And by this, and also by the abundance of cheap cameras, we can collect easily a lot of data. And we can also provide ground truth annotations for those data, because average humans are good at annotating images, for example, recognizing what type of objects are in an image. So in this sense, like computer vision plays a really important role also for self-driving. And here I will go a little bit into coming from like from early times about intelligence and how it evolved. And just because many sciences consider them that they originate from ancient Greeks, it means like also some already an ancient Greek philosopher was thinking about problems they want to do. And if we are in computer science, that's a little bit difficult to trace back ourselves to ancient Greek philosophers, because the digital computers were only invented in the middle of the 20th century. But I will also try to go a little bit back in history. So we have like human, or we can also say also animal intelligence. And we know this is a good example of that there is some system, a biological system, which can is to survive in the wild. And what we can say is mostly that most animals or humans, we have very good pattern recognition abilities, especially the visual ones. And we can also understand it that there was a high evolutionary pressure. Just if there is a carnivore animal, it has to be able to hunt down its prey. And for this, you usually need very good vision. And this was also kind of an arms race to get better and better vision for animals and thus also humans. So, and then we arrived at, okay, we have like also we humans have a very good visual pattern recognition capabilities. And this is kind of happening automatically. When we look at an image, we look around, we don't have to think about, we instantly can recognize objects. And this is also like computer vision try to tackle this, and they try to solve similar problems. And as like also in ancient times, also now we try to use these kind of pattern recognition abilities to learn about the world. And this is how also philosophy and then later science emerged. But what turns out that usually these pattern recognition systems, they can be a little bit overdriven. I would say one example is this, that if we have like these, we have these zodiac signs in the star, we have certain patterns, and people started to see patterns into those. Despite, for me, it wouldn't be obvious, like, really to recognize these patterns in the stars. So this is an example where like the human brain and so can a little bit also hallucinate, so recognize patterns even if they are not necessarily there. And then, so this was more an ancient way of learning about the world, but then came the scientific revolution, which is usually dated back to the end of the medieval ages. And they say that very one important statement was made by Galileo Galilei, and it was basically, if I quote it properly, that philosophy is written in this grand book, the universe, and it's written in the language of mathematics. So that was the time when they decided, okay, we cannot just rely on our own brain and our own intuitions, but we have to come up with some formal method like mathematics to learn about the world. And good examples for this are like, for example, Newton's equations or Maxwell's equations. And these are also, what is important about them, that it's like that we can describe very complicated things by very few mathematical equations. And then we can derive a lot of other information out of this. And this was kind of becoming the scientific approach. And this was also driving a lot of developments. And then here I would like to mention one of those which is still relevant today and can be considered like very important of one of these classical methods which I mentioned. It's called least squares, which is basically a solution for overdetermined systems. And sorry, if for someone it's a little bit scary, it will get a little bit more mathy, but I try to keep it simple. And this kind of method was invented by Carl Friedrich Gauss, and the main application was, so the first successful showcase of really this method, how powerful this method can be, is that there was a new asteroid discovered, and then Gauss, just using 22 observation, could predict how this asteroid will appear from behind the sun, and he was later right. And this is also the method which is used, for example, in regression. if people start to study machine learning, it's in very early courses they can learn about regression. And why I say this, also least squares is still something important, relevant today. For example, now many of us have robot vacuum cleaners, and those use a technology called simultaneous localization and mapping, which basically helps the robot to navigate around and find its way. And these methods are all based on least squares. So if I would extrapolate a bit, I would say that basically robot vacuum cleaners are a very fancy way of least squares. But yeah, there is some that's some simplification. But I mean, the important part is that technologies which are considered like AI now are also based on these classical methods as well. All right. So just to give you an intuition what is this least squares is about, I will give a toy problem. Let's consider that we want to measure the level water somewhere, and we can do multiple measurements. But what we have to assume that these measurements are noisy because there are some ways, for example. And just to keep the problem simple, we can assume that during the time when we make the measurements, the water level doesn't change. And then comes the question: how can we come up with a more accurate estimation of the water level? And then this is also where we can use least squares. And if we take this example, 1 minute, I will get my pointer. Yeah, that we can have like, let's say we make like 3 measurements. One of these 10.4, 9.1, 10.2, and this can be, for example, meters, but really the unit is not so important. And then just deriving equations from linear algebra, we can go up to, okay, what will be our solution? And here I don't want to really go into the details, but we can then, using these equations, we come up to a solution which is like, okay, based on these measurements, we get the results of 9.9, let's say, meters. Okay, and then we also try to consider this as more, another way to consider this problem is more from a probabilistic approach. And this would be that we can say that we have a water level, but there are some uncertainties, and the mathematical way to express uncertainties are probability density functions. And then we can use one very common probability density function is like a Gaussian function, which looks like a bell curve here. So this is like the distribution over the water levels. And when we say that we have like multiple of these measurements and they are independent, we can write down these as this kind of likelihood function. And then by doing some math, we will arrive that when we want to find that kind of value which has the maximum likelihood, is by some derivation, we arrive to a formula which will be like basically summing up all our equations and dividing it by our number of equations. And for many of you, this will look familiar because that's the well-known equation of like computing the average. And this is also one way kind of that, okay, we have this, I think already in high school, we can learn, for example, in physics that, okay, if you have some noisy measurements, you should do multiple measurements and then take the average. And there is kind of the theoretical background of it. And this problem also, we were looking for the maximum here along all possible values for this function. And this could be also considered that we take the minimum of this negative value. And then we can also basically define that there is some energy function and we want to minimize that. And like minimizing energy function is also something very typical in sciences, for example, in physics, but also energy function can be different name would be a cost function. And that is also widely used around many areas. Okay, and now I'm going back from like then these classical science methods to coming to machine learning. So we had this that now we arrive at sometimes around the 70s, 80s, where people started to do computer vision. So we wanted to do that. We wanted to understand images. And we had this background which comes from like classical sciences that we want to have like concise equations and then deriving solutions from that. And people believe that this should be also possible for like images and so. But it turns out that we were really underestimating the difficulty of this problem. A good example how much this was underestimated is this MIT summer project from 1966. So it's a pretty early project at MIT, like a top elite university. And they were basically proposing, for a student summer project that they should solve this perception problem. It's about understanding images. And we can say that even after decades of research, we were not really succeeding with this, and there's also still very much ongoing research. And in the early days, there were more methods like this canny edge detector by using some heuristics, or even like other methods where we used like more well-defined knowledge from, for example, 3D geometry, which we would leverage. And the people really tried to solve this problem by having some derivations, some equations, heuristics, but all these methods were not really successful. So basically at that time, when you had the general image, which, for example, you take on a street and you would like to recognize some person, that was basically not possible with all these methods. And just also because I started to work on computer vision before the deep learning revolution, and at that time, really nothing was really working. So sometimes even people had this that you try to solve a problem, for example, detecting pedestrians or cars in an image, and then you made some methods for that, and that method was usually so noisy that sometimes people were joking about that you make a game that you show your results, like you show the inputs, you show the outputs which your method produced, and then people have to guess what kind of problem you try to solve. Because it was just so noisy, the result, that it was not even obvious what problem you tackle. And then because, so this was kind of a way which was not successful. And then people started to look into machine learning, and especially what became successful with deep learning. And here, we kind of break with the desire to have like concise equations between the input and the output relation. So for input, we can consider things like an image. Here, for example, it's an image of a cat, which for us humans, it looks easy that, okay, there is a cat, it's obvious. But if we would look down, what's actually the data, what a computer sees, it seems it's just a big bunch of numbers. And even as humans, recognizing that how these numbers make up it to being perceived as a cat is pretty difficult. And then our output is like a label, okay, it's a cat. And then the machine learning approach was that instead of coming up with some heuristics, some knowledge where we define and find a function which would solve this relation, we let the computer to search around and we provide a very big space of possible functions. And then basically the machine learning method has to try to search what is the best possible function which can do this. And then one very advanced method of these are deep learning. And what is important that usually you compute kind of a function. This is in deep learning. You compute a loss. This is basically measures some kind of similarity between your output and the ground truth label. And then you can compute gradients and update the parameters of this function. It's like really like turning small knots on a system until you have a good setting. And this kind of approach became a really big success in computer vision, especially with deep learning. And then, for example, for problems like image classification, where you are given an image and you have to describe what is in the image, this was working super well. So this was kind of the time when people were like, okay, to understand these complicated data, like images, or another example would be like human speech, we have to turn to machine learning. And nowadays, the best method is like deep learning. And then, because we saw now that, okay, deep learning is such a big success, then kind of the questions that if we are faced with a problem, what kind of methods should we use? And here I make a little bit comparison, like what we can consider when we have this question. So first I start with like classical methods. Usually they can be framed like as an optimization methods. So we are searching for a variable and we are searching for a value which minimizes a cost function, or we can also say energy function. So this was really also similar what I show in that toy example. And there is some benefit that we don't really need the training data. So that makes in many cases the problem simpler. And when these approaches can be still successful are, for example, when for some reason we cannot gather training data, but we have already a good understanding of what's happening, how really the relations are defined. And examples, something related to self-driving are, for example, when we have to reason about things like 3D camera geometry or state estimation of like moving objects. So these are good examples where these classical methods are still very heavily used. And then there was the other approach of deep learning. So in deep learning, we had like a lot of parameters which define a very big family of possible functions, and we need to have a large amount of data to compute these kind of relations from data. And it can be adapted to any type of data. But where this can be successful is where we have the opportunity to collect this huge amount of data and also have run through for that data. This was typically the case for computer vision. And the reason why I said is because we have a lot of data, and getting like good ground truth by human annotators is quite cost effective. And then I asked at the beginning, what is the question, which one should we use? And here I would argue that, okay, we don't have to necessarily make this decision, but we could also combine these to use these together. And how such a system would look like, that we basically had at the beginning a deep neural network. It outputs us certain features, and then we define this minimization problem, optimization problem on top of those features. And what is nice, that into this minimization, we can encode our prior knowledge. And here, in this case, we still need training data, because training the network needs data, but we need less data. And where these kind of systems are successful, when we want to have a system which is also end-to-end trainable, that we can define the final ground truth value at the end of the system. But also this can provide something which is still interpretable, because usually at the output of the network, we are able to define features which a human and engineer can understand. And one example where this can be successful were systems like this new research about 3D geometry, also for methods for the simultaneous localization and mapping, or like performing the motion planning of self-driving cars. And then I will go over that. So here I was a little bit arguing that we can also use this hybrid system. And here I will want to show you a very simple toy example for such a system. And then let's go back again to our problem with measuring the water level. And let's assume now we have a system where we have this water level. We take a camera, we put in the camera image into, for example, a CNN, and then the CNN can put an output of, okay, what is the estimation of this water level? And I would like to emphasize that this is a toy problem. So if you want to really tackle the problem of measuring the water level, there are probably better solutions. But this is more as to teach us about how this could work. And then basically we can make this deep neural network to predict the water level, which can be considered as a regression. And then it comes that, okay, if we have multiple of these images, how can we aggregate the output of these deep neural networks? And then just going back, what I mentioned, we can use least squares, which results in basically averaging the outputs of this deep neural network. And so I mean, basically you could also, people would come up that, for example, if I have 10 images, I put also all the 10 images into the deep neural network, but such a solution usually would end up in like requiring much more computation, and gathering data for them would be more difficult. So in many cases, already using our existing knowledge can be beneficial. And in this case, our existing knowledge would be to use least squares, basically averaging over the output of the neural network. And then, because we can say, okay, this is already a hybrid network, but it sounds so simple that people would be like, hey, okay, this is not a big deal. But then I would like to go a little bit into a more advanced level and kind of ask the questions, have we considered all the information which is available? And I guess from the case that I asked this, we can say no, we should do something better. And I will show. So for example, we could look in the image and infer that in some cases our measurements was less noisy, because there were small waves. In the other case, we can say, oh, there were big waves. And this is also something the camera could see. So this is something what we could observe. And then we can basically also frame the problem that now we get the image from the camera, we use our neural network, but now we move on that the neural network will predict a distribution. So it's not just a simple value of output, but really a kind of a family whole distribution of them, which can be also parameterized, for example, by a normal distribution. And then in this specific case, we can consider this that we moved from a normal least squares problem to a weighted least squares problem. And here in this case, we get similar equations, but with a little bit of an update. What is important that basically we can consider weights, which are the inverse of our standard deviation. It means that for values where our uncertainty is small, we give a higher weight, and for very noisy measurements, we give a lower weight. And by putting these also into our framework of least squares, we get now also some solution. And what we can see, so let's say our measurements are the same as before, but let's now say that we had like one measurement which had like small noise, one with these big waves had like a bigger noise, and then we again have something with a smaller noise, and we solve for this. We see now that we get something a little bit of different results. So now our final prediction is closer to the values which had bigger certainty. So this was the original when everything had the same weight. And what is important here that these weights were coming as an output of our neural network. So these were trained and the network was learning it. It has learned to look on some features, something like the waves, and use that information. And we can say that this is now something, a hybrid system where we both use deep learning and classical methods, and we can train those together. And then just the end, as I come close to my I want to just give some examples where such methods can be used in problems related to self-driving. One of them is like where we have to reason about camera geometry. This is also where we have good mathematical foundations, how the relationships look like between a 3D point and a 2D point. Or it can be also something where we reason about the motion of different participants in the traffic. And we also have now more physics-based assumptions. For example, a car cannot drive perpendicular to its direction. So this is a valid constraint. This is also why, for example, parking is a difficult maneuver, because you have to really plan in advance how you can take some maneuvers. And then just a very final slide, I would like to show some systems made by us, by Continental, with deep learning, how we tackle different type of computer vision problems. Here you can see that we are doing semantic segmentation. This is the task that the system gets an input image, and we want to say for every pixel here what type of class it belongs. For example, here the blue color encodes that, oh, hey, there is a car over there. Here we show some examples of like an object tracking method where we have to put like bounding boxes around cars, and we have to reason about if that car is the same as on the previous image, and we encode this by different colors. So as long as the color is the same, it means that we can track an object properly. And here one more example of some interesting task in computer vision is like predicting the depth, how far a pixel is. So as I mentioned, this is something which just from the image we cannot know it, so we have to we have to some additional information to get that information. And here this is an example for fusing LiDAR sensors and camera sensors. But my colleague Robert will talk about this. So if you're interested in this, then let's also go for his presentation. And by this, I would like to thank you for attention. As a conclusion, what I'll try to show you that we can also use kind of these more classical methods and deep learning together. And if you want to talk about this a little bit later in detail, you can contact me on LinkedIn. And now I'm ready for your questions. And sorry if I was a little bit over time.
Thank you so much, Gellért. Actually, the timing is great. Thank you very much for your fascinating talk. We have a few questions for you. But first, audience, keep in mind, we would like your feedback for Gellért over on the polls tab. So jump over there, give him some feedback, and that would be appreciated. And now let's get to some questions. So Gellért, the first question comes from Jeffrey, and it came in about 28 minutes ago. So I'm not sure if you addressed it in your talk or not. But the question is, can you give any sort of assessment about how close we are to level 5 automated driving?
Yeah, so if I go back to my slides and take this, yeah, so level 5. So my assessment would be that level 5 is quite far away. So I would say at least 1 decade. And also because now companies are working more on really to get to level 5, we have to solve first like many problems in level 4 or level 3. So I think level 5 would be that, okay, you buy your own car and you can go, I don't know, to a wedding, to somewhere in some different city, and you can just, I don't know, drink and then just sit into a car and the car brings you back. I would say that this is quite far away. But what is closer is really advanced L2, L3 systems, which are very important because these can prevent collisions and fatalities now. And also what is maybe a little bit closer is L4 system. So in limited areas, you can use these autonomous systems for like robot, like taxi services.
Thank you very much. Our next question comes from Peter, and he says, Tesla aims to use solely deep learning, so-called software 2.0. Neural networks are lacking in explainability, but they're very accurate. Can you give some thoughts on that trade-off and on Tesla's decision?
So yeah, so thank you for the question. So first, I would not like to comment on any of our competitors. What I can say that, as to my knowledge, really what are now systems out there, they are both leverage deep learning and also these more classical methods. So it's a combination of both. So I would say that really systems there are going more into that direction I want to go, that we use kind of both. But what there is important that, okay, how can we really make some good trade-offs, how we can train these jointly?
Okay, thank you. Our next question is from Janos. Could the fusion of a deep learning and classical method be used to mitigate the effects of adversarial examples?
So I think, yeah, that's a very good question. And I would not say that I definitely can know the answer, because usually what people observe that in each case where you have like deep learning, their adversarial examples can appear. So I would say it's not guaranteed that by using these hybrid methods we can avoid these kind of examples. But what such a system could provide at the end of this system, if there is some adversarial example, it usually would mean that we have something like a big outlier, and this more classical method could filter that outlier.
Thank you very much. Our next question is a bit of a long one. There's 3 parts to it, but I'll give you the first part.
Yeah,
the paradigm.
Break it down.
Sorry?
Yeah, just break down the question so
okay.
I don't forget the first one before.
All right. So the first question, the paradigm is learning more data, more computing, more layers. Tesla's autopilot needs 70,000 GPU training hours, 48 networks, 1.5 petabytes of data in order to train. And by contrast, humans can learn to drive roughly in 30 hours. Can you see a paradigm shift or innovation in this area?
I would say that, yeah, thank you for the question. So on the long term, we have to come up with methods which can learn better. And so really, I would say this is nowadays what's a big challenge of us is make the system. So deep learning systems are very good at learning from big data, but they suffer from generalization. So humans are really good at generalization, that with a few trials, we can learn new we can solve new problems, and this is now missing from deep learning. So I would say that as we are going for really these systems, there will be methods which can address it better. But I would say what is difficult to see if we need a paradigm shift or not. So this is something which we will only be able to assess when we are looking backward. Okay. So it's a little bit like an unknown, and I guess it's really exciting that how this can be how this can evolve.
Definitely. And the second part of this question is, could we achieve human level efficiency with a hybrid approach?
So I would say that here, this hybrid approach also, so some of the parts are using the deep learning, which is there nowadays. But so I would say that as things are now, they are not obviously a solution for the problems today. But I think also problem formulations like these can also help in leveraging data better. I guess one of these are like, this can also bring us closer to like self-supervised methods, for example, where we can leverage redundancy of the data, which is, for example, present if you look at a video and we have to reason about 3D. So I guess I would say that as these methods are nowadays, they don't solve this problem, but they can be an exciting new direction, which can finally bring us closer to learning with less labeled data.
Excellent. Our last question comes from Ashima. She says, can you please brief on how to convert these black box neural nets to white boxes in order to ensure more trust in the insights by deep learning?
So I would say that, like, if you look at this pace, that how we want to, so my field, I don't really work on the problem of turning the inside of these networks into something interpretable. What I can tell that one approach is that at the end of these networks, we can have something interpretable, like having objects. And then when we put these together, and we put this into more this classical method, we have some better knowledge already there. So I would say it doesn't solve the problem of resolving the interpretability inside the network, but it can help us to break down the problem. So we don't have to look at the very big problem, like taking in an image and putting out like how a car should accelerate or not, but we can put it into smaller problems. And that can already be helpful when we work on a big complicated system.
Thank you very much. One more question just came in, and I think it's a juicy one. I'm curious to what your answer could be. It says, there is a general distrust towards AI. I'd imagine lawmakers don't hold AI to the same standard as humans. With this in mind, reasonably, how much better does AI have to be considered an alternative to human drivers? And how can we measure these aspects?
Yeah, so yeah, this is also something complicated question. And I would also say this is not really on the engineering level. So this is some question which can be better answered by the entire society. So it's like, when will society accept AI, or especially a self-driving car, to be safer? And I see that in this case, what we have to look is really on the statistics. Like when we can really reliably show that these systems just save lives. And at that point, I guess people, maybe the society will slowly, so once these AI methods have enough trust, people will start to see the advantages. And then at some point, they will say, okay, we accept that, I don't know, accidents can happen all the time, but if there are less accidents, that's beneficial. So where that threshold is, does it have to be 10 times, 100 times? I don't know. And I think this is also more what will depend on the society. But yeah, I see that over time, this will happen.
Great. I want to thank the audience for all of their interesting questions, and thank you for the fascinating talk. And as a little thank you from the organizers, we have this beautiful hand-drawn, one-of-a-kind portrait of you. We're going to send that to you in the mail. So look forward to that. And once again, Gellért, thank you so much for being with us today. Appreciate it.
All right. Yeah, thank you.
Thanks.
Goodbye.